Hopefully you've had an opportunity to try the last of our practice problems. I'm now going to walk through a solution for them. So we are going to try to calculate the enthalpy of the reaction for this methane combining with water to form methanol and hydrogen gas. Um, and the question is it really possible to do this? Because this is actually one of these fun questions in chemistry, right? You have these large deposits of methane gas, usually in remote regions, and not at all anywhere near a plant that would be able to process that into a more useful material. Like having a carbon feedstock like methane would be really valuable instead of using a fossil fuel. So one idea is always, can we convert methanol on site or methane on site into methanol, which is a liquid, and so much easier to transport than a gas. And then we could like have a pipeline of methanol to a plant where it could then get processed into something else more useful. And so this is really answering the question like, is this possible? Is it theoretically possible under the right conditions? So we're going to try to see if this is what the enthalpy of this reaction is. And so we have a lot of different things that we can use that are standard enthalpies of reaction. And I pulled these from a table. And this is usually what you're confronted with. You have a reaction you're interested in, and you have tables and tables and tables of standard enthalpy reactions that you're trying to see if you can actually use that information to learn about what you're interested in. So the step is to try to take your most complicated molecule and find it in one of these reactions. So I'm going to start with my methanol, and I'm looking down top to bottom, and I'm trying to determine which of these reactions would contain methanol. And I see only one right here, third one down. Okay, so that's where my methanol is. Next, I'm going to go look for my methane and methane gas. And so looking through these, I see I actually only have methane gas in one of them as well. It's right here. And so I'm going to go through and just try to find, it's like playing a search game for my molecules I'm interested in. All right, how about water gas? I've got two interesting ones. I have water gas and I have water liquid right here. So I have to make a choice. We always want exactly the same thing. So I'm going to ignore the water one, and I'm going to go with the one that has the water as a gas. And then lastly, let's look at hydrogen. And I have hydrogen listed right here and right here. But I also can see that it's in here, 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 and here. So hydrogen gas is in every single one of these reactions. So I am going to go out on a limb and see if I can't use the least number of equations to solve this problem, and hope that I get a hydrogen molecule as part of my manipulation of the other ones. Because when I look at these, I don't want to introduce water as a liquid form into my reaction. And I don't want to introduce ethanol because I won't have a way, like I don't want that in my final answer, and I won't have a way of getting rid of it. Same with the C2H2. So I'm not going to try to use those reactions at all. So let's start now manipulating these. So first off, I can see that I have my CH4 is on the product side rather than the reactant side. So I know I'm going to need to multiply this one by -1, which will multiply my enthalpy by -1. Now, the coefficient is the same. I have one methane and one methane in both of the reactions, so that should be enough. So that's going to give me an enthalpy of reaction that's positive 74.848 kilojoules. Now, for the water, I have the same number of coefficients, 1 and 1. Great. So I don't need to multiply it by a larger number. But again, it is the water gas is on the product side in this reaction I'm looking at, and I'm interested in it being on the reactant side. So I'm going to multiply this by -1 too. And that'll give me an enthalpy that is positive 241.8 kilojoules. Now, for the last one, the methanol, it is on the right side of the equation. I'm interested in my methanol being a product, and it is in this reaction, and it has the same coefficient, so I don't need to multiply it by a 2 or a 3. So I'm going to leave this one alone and do nothing to it. So I'm going to flip and then add these all together. So I'm going to write them out. I'm going to hit pause while I write all the reactions. Actually, Actually, I'll record the flipping just so you can see what I mean. So I'll start with the first one. I'm going to flip it. So my CH4 gas is now a reactant going to carbon solid plus 2 hydrogen gas. And I'll flip my other one for the water. So I've got water as a gas as a reactant now going to form hydrogen gas plus half an oxygen. And my methanol one, I'm going to keep the same. So it'll just be carbon solid plus 2 hydrogen gas plus 1/2 oxygen gas will form CH3OH liquid. Okay, I'm going to take these and sum them up. So they're all on the same side. There we go. Give it a little bit more room. So I have CH4 plus H2O gas plus my carbon, that's a solid, plus my 2 hydrogen gas, plus my half of an oxygen. It's a lot to write out on each side. All right, now now I do my products. So for my products, I have carbon solid plus my 2 hydrogen gas, plus my H2 gas and my 1/2 oxygen. And I'm just going through each equation. And then finally my methanol. Okay, so now I'm going to highlight the ones that I'm interested in again. I'm interested in that methane. I'm interested in the water. I'm going to really hope that these don't completely all cancel out. I'm interested in the methanol. And I'm also interested in the hydrogen, which I have in a couple places here. So let's cancel things out and see what this reduces to. So we're going to just cancel out anything that's the same on either side of the arrow. So right away, I can see that carbon solid is on both sides. The 2 hydrogen is on both sides as well. But that leaves 1 hydrogen left on my product side, which is great. That's exactly what I want. I have 1/2 of an oxygen on either side as well that can cancel. But my water, my methane, and my methanol don't cancel out. So this reduces to CH4 gas plus water gas, which forms my 1 hydrogen gas plus my methanol liquid. And that's, oh, sorry. That's exactly what I was looking for all along. So great. That means that these manipulations I made work fantastically for getting me to the reaction that I'm interested in. I'm going to take the sum of those enthalpies of reactions after I manipulated them, and I am going to get a value that is plus 78.048 kilojoules. And that really means that positive enthalpy means I'm going to have to input energy into this reaction to make it happen. It'll be an endothermic process. It'll require my reactants are more stable than my products. And so they'll be at a higher internal energy. I'll have a positive internal energy change. All right, and now we're going to look at our last practice problem, and this is calculating the enthalpy, the standard enthalpy of reaction from the standard enthalpies of formation. And so the reaction that I'm interested in is this ammonium plus oxygen is forming NO2 plus water. So I'm going to set up my equation, and then I'm going to find my values in a table and plug them into it. So remember, I am for my enthalpy, my change in enthalpy of the reaction, it's going to be equal to the sum of the coefficient times the change in enthalpy of formation for any of my products minus that sum of the coefficient times the change in standard enthalpy of formation for my reactants. So looking at my products, I have this NO2 and this H2O. So I'm going to write this out. It means it's going to be that 4 times the standard enthalpy of formation for NO2 plus 6 times that standard enthalpy of formation for water. And I'm going to make sure that I'm finding the version that has the same phase for this when I do it. And that'll take care of my products. And from that, I'll subtract the reactants. So I have 4 ammonia. So I'll have 4 times that standard enthalpy of formation for my NH3, plus the 7 times the standard enthalpy of formation for oxygen gas. All right. So now I'm going to go ahead and go to my table and find these values. So when I look up a table and I look up NO2 gas, the enthalpy of formation, I find a value that is 34 kilojoules per mole. For my water that's in the liquid state, which is important, it's different, different than the gas or solid, it'll have different values. It's negative 285.9 kilojoules per mole. Now I go and look up my ammonium standard formation, and that's going to be a negative 46.0 kilojoules per mole. And for my oxygen, it's in its elemental state, so that's just going to be 0, which is great. Simplifies it a little bit. So my reaction is then going to, or my equation I'm going to plug into my calculator is essentially going to be 4 times 34 plus 6 times negative 285.9 minus my 4 times negative 46.0 plus 7 times 0. So that'll just be 0. Plugging that into my calculator, I get a value that's negative 1,395 kilojoules. So that'll be my standard enthalpy for reaction for this equation, which I was able to pull from a table, which is really nice and handy.